Welcome. So this time we're going to look at what happens when you have gradients of density in a fluid, and in particular this is called a buoyancy wave or an internal wave in fluid mechanics, and it has a relationship to instabilities. So if you have a wave, you can see when the frequency becomes imaginary, you have a growing or a shrinking wave, and this is called an instability. And the same ideas and the same physics in some cases will turn up in both plasma physics and in neutral fluids. So we'll look at this is a common situation in the atmosphere. So you've probably seen the results of this already, and so I'll just describe what we're talking about here. So this is where you have a case where you have a vertical direction. I'm going to call y. So this is just height. And you have a horizontal direction, we're going to label x, and you have a density which varies. So density rho is some function of y, and we've seen for equilibrium that this occurs in a stationary atmosphere where you have the pressure at the bottom of the atmosphere is higher than the pressure at the top, and through the ideal gas law the density is also higher at the bottom than at the top. So you have a gradient where if I plot the density on this graph here, so density is now essentially a decreasing, an exponentially decreasing function of height if temperature is constant. So this is height, and then this is rho. So rho is decreasing as you go up. Now what happens in the atmosphere is if you have an equilibrium like this, and then it's disturbed, you end up with a wave which oscillates up and down and side to side, as we'll see it shortly. For example, if you have a mountain or hill and you have a flow over the top, so air is flowing over the top of this mountain, the air that comes over the top here is pushed up, and as it comes out the other side it'll drop and then it'll oscillate, and so you end up with wind moving and oscillating. And quite often what will happen is that the tops of these will form clouds. So as the air moves up, the water condenses and forms clouds, and so you see these stripes of cloud across the sky. And you've probably seen this many times. So this kind of explain why this happens. This is a old mountain. Okay, so air is moving over the top of the mountain and oscillating, and you'll see it's oscillating because there is a density gradient. Okay, we can try and analyze this by doing the same linearization process we did previously for sound waves. So the idea is we take every quantity we have, so we have density is some function of y, and we split it up into two components. So we split it into an equilibrium component, which is this function of y, so this is the equilibrium part here, plus a perturbed quantity, delta rho, and this is going to be the oscillating part here. So this is the part of the wave that's oscillating. And then we have a velocity u, which again is a u naught, some equilibrium velocity plus a perturbed quantity. Now what we're going to do for this kind of problem is we shift into the frame of the wave, of the wind, and so the equilibrium velocity we're going to assume is 0. So here we're going to assume it's static. So this can still handle this case, because if you move along with the flow, the average initial flow is 0, and you just have a perturbation, which is the vertical wave. And the same for the pressure. You have a P is some equilibrium P naught, which here will be some function of y as well, like the equilibrium density, plus a perturbed pressure. Okay, so now we can essentially put this into our equations. So the most important one here is the momentum equation. So we have an equation which is basically the mass density, u by dt, so the same as we've seen several times already. And this is obviously the change in momentum, and this is the forces on the parcel of fluid. So we have the gradient of pressure as usual. Now also we have another term coming from the gravity. So I'm going to rho gravity times mass density here. And now gravity is pointing downwards, so I put a minus sign here. So g is downwards. This is g, and it's downwards in the y direction. Okay, so g is pointing down. Okay, So then we can linearize this equation as before, and we essentially substitute these expressions into this formula. And what we end up with is keeping only the terms which involve a single perturbed quantity. So every term which involves only one of delta rho, delta u, or delta p. And all the terms involving two quantities we discount as though being small, because those are nonlinear terms. And so if we do this, we end up with essentially a rho naught. So here we have a delta u. Here we end up with essentially nothing here because there's no equilibrium flow, and so the u naughts dot grad delta u's all cancel out, as that actually goes to 0. Then here, this part, we just have the equilibrium part here and the perturbed, so the equilibrium part goes to 0, or cancels out with all the other equilibrium parts, so delta p goes here. And then here, g is obviously a constant, and rho is a perturbed quantity. So we have g times delta rho. Okay, so that's the linearized equation we're going to solve. And then to do this, what we're going to do is we're going to differentiate this equation in time. So the same trick as we did for the sound waves. So we can differentiate this in time, and then we'll have expressions for delta d delta p by dt and d delta rho by dt. And then we can substitute in the other equations for that. So let's do that. So we have rho, and then differentiate this in time again. So we have d2 delta u by dt squared, and that is equal to minus gradient, so d delta p by dt, minus this gravity d delta rho by dt. And then we can substitute in the other equations for these expressions. Now for now, what I'm going to do is neglect this pressure term. So neglect for now. And you'll see why very shortly. It'll turn out we get a very similar answer, but this time is important for getting the full answer. But for now we'll neglect it, just to get the basic physical picture for what's happening. And so we just need expression for this. So we have the original density equation. So mass density is d rho by dt plus u dot grad, we'll write it in this form, and it's minus rho dp. So for now we're going to also assume that this is 0. So we're going to assume that this is incompressible. And this can be shown to be a good approximation if the flow speed is small compared to the sound speed. And so here we're looking at slow variations, slow motions, and so this is a good approximation. In one of the other videos I'm going to show how good this approximation is and why it's a good one. And so for now we just have these two terms, and so we linearize this, and this is just d delta rho by dt. This equilibrium flow is 0 in this case, so we just have a delta u dot grad and then a rho naught equals 0. Okay, so I have this expression here for delta rho, or d delta rho by dt, which you can substitute into this formula up here. So let's do that here. So we have the rho d2u by, so it's delta u by dt squared, and then up here we have the pressure term that we're neglecting, minus, we have a minus g, and then we have this d rho by dt, which is just another minus, so this gives us a plus here. Then we have a delta u, well, d, so g, and then we have a delta u dot grad rho naught. So rho naught. That's the rho naught. Okay. Alright, so this is starting to look reasonable. So we have a second derivative of the velocity, and we have a term involving the velocity here. So what we can do is we can look at this in one dimension. So we can look at what happens when you have, I'll draw the axes. This y is up and x is horizontal. And so we have, say, a wave just like this. So we have a perturbation which is in y. So u is basically in the y directions. So we take the y component. So this is the vertical components of this equation. And what we get is that rho naught d2 uy by dt squared is, here we have g, we have delta uy, so we have a d rho naught by dy times delta uy, it's delta uy. Okay, and this is now essentially an equation involving the second derivative and this density gradient. And so now we have something which looks like essentially an exponential. And so we have a d2 uy delta y divided by dt squared is g over rho naught d rho naught by dy delta uy. And this we're going to write as minus n squared delta uy. Right, n is the frequency of the oscillation, so you can see this. So this is minus n squared. So d rho by dy is negative because density is dropping with height, and so g is positive, so g pointing down, and so this is this whole thing is a negative quantity, and so n squared here is positive, and the solution looks like delta uy is proportional to e to the I n t. So n here is a frequency, so you differentiate this twice with time and you get a minus n squared coming out the front here. And so if n is positive, then this is an oscillation, so n greater than 0. So so this happens if d rho naught by dt is is less than d rho naught by dy is less than 0, so if density is decreasing with height, then this frequency is positive, and this is an oscillating wave. And that's what happens if you have a got this. So then we have x this way, y like this. We have a high density here, and I have a low density here. And now if we push the fluid upwards here and downwards there, what's happening is you have an increase in density here, and a decrease in density there, and there's a restoring force, so the gravity now pulls this high density region down and pushes relatively pushes the low density up, so it feels a buoyancy force which restores this to its original position. And so there's a force which is pushing this down and pushing this up, and so this tends to accelerate downwards, and you end up with a restoring force the other way, and this will wobble, this will oscillate up and down at this frequency n, where n is just minus g over rho naught d rho naught by dy. Okay, so what happens if rho naught is turned upside down? So what happens if n is actually imaginary? So n so this happens if d rho naught by dy is less than 0. So sorry, this happens if d rho naught by dy is greater than 0. So if this is bigger than 0, then this is negative and n becomes imaginary. And if n is imaginary, then this becomes e to the something times t, e to the real number times t. And then we get essentially growing solutions. So growing. And this is what happens when you, if you have, say, water on top of oil. So you end up with essentially bubbles rising up, and the higher the bubbles rise, the less the restoring force is, and so they continue to accelerate upwards. So you have a case where if this is x and this is y, what's happening is you now have high density. This is high density on top and low density on the bottom, and gravity is pointing down. And so now you have a bubble of low density fluid going upwards. So as it rises upwards, the density you can see in this in the equation here. So it's the perturbed density, which is leading to this term in the equation. So this is the gravity force downwards. So as the density goes down, say at a fixed location, so we look at this location here, for example, as this bubble rises up, the density at this location is falling, and so the restoring force, the downwards force due to gravity, is reducing, and as that's reduced, the net imbalance gets bigger and it accelerates upwards, and so you get a bubble of low density fluid rising upwards and high density fluid falling. And this is essentially the basic physics of a Rayleigh-Taylor instability. And this kind of instability occurs in many different fluid systems, including plasmas. The general term is an interchange instability. So we have one fluid with a high density, and it's energetically favorable for it to exchange or interchange with a low density fluid. And so the two fluids will swap locations. So if you have oil and water, if you try and put the water on top of the oil, it will go unstable, it will produce these bubbles, and it will end up with the high density on the bottom, so we'll end up with the water at the bottom and the oil at the top. Okay, so that's the basic physics of what we're looking at. So we have either waves if the equilibrium density is decreasing with height, or an instability if the density is increasing with height. And so now I want to go back to this equation where we neglected this pressure perturbation. So that's not the one. So now I want to go back to this equation here where we have the momentum, and we neglected this term which is due to the pressure perturbation, and we just concentrate on this buoyancy force. This pressure perturbation actually has an important effect on the result, although the same basic frequencies and the same basic physics occurs. So I want to just include these other effects. So what we need to do is we need to introduce the additional constraint. So we need to use the fact that we've assumed divergence of velocity is 0. And so this means that we can write in 2 dimensions, in x, y, we can write that dux by dx plus duy is equal to 0. Then we differentiate this in time. There's a few slightly strange steps, but bear with me for this. So we differentiate this in time. So d by dx of in time and x, or time and y commute, so just move them through. So now we can substitute in here the equation for the horizontal velocity ux, and so we can write down that dux by dt is, now we have minus 1 over rho naught, and then the pressure in the x direction, so this is d delta p by dx. And so this goes into here. Rho naught doesn't depend on x, so this will just go straight through the x derivative here. And so we can write down that we have, so we have 1 over rho naught d2 delta p by dx squared is equal to this. So it equals d by dy duy by dt. Okay, so this is going to be useful very shortly. So now we go back to the momentum equation, which in y we had d2uy by dt squared, and that was equal to minus 1 over rho naught d by dy. Then we have a d delta p by t. And this is the term that we ignored previously. Minus delta. And now we can just put n squared here. So this captures all the terms involving gravity in that term. So that's the term we had before, and this is the term we're now adding. And so what we want to do is use this expression here for d delta p by dt by dx squared, and use it in getting rid of this. So the trick here is to differentiate this twice with respect to x. So we're going to apply d2 by dx squared to this equation, and because the d by dx goes through rho naughts and d by dy's and d by dt's, this will let us get d2 delta p by dx squared. And so we have the d2 by dx squared of d2 uy by dt squared, and then we have a 1 over rho naught d by dy of d delta p by dt becomes d by dt, and then we have a second derivative of delta p in x squared. So this is d2 delta p by dx squared, which of course we can now substitute into here. Minus, as before, you have d2 uy by dx squared times n squared. Okay, so this now gives us essentially a way of substituting this expression here. So this expression, which we're now going to substitute into here. And so we have d2 by dx squared d2 uy by dt squared. So this has given us a constraint. What happens with the compression? So that this is enforcing the incompressibility. So if we have here, so we have minus 1 over rho naught d by dy, a d by dt, and now I'm going to put the rho naught over this side. So now I have a rho naught d by dy of a du by dt. Okay, so you can see we can start to get terms that we can use. Minus n squared d2 uy by dx squared. Okay, so now this takes a bit of manipulating. So the d by dt's, we can move through all these quantities, so rho naughts and d by dy's, and so we can group that together into a second derivative in time. We have a one of rho naughts and rho naughts here, which can't in principle move through d by dy's, so we have to keep them for now. But we can group together the d by dt's or into the second derivatives here. So what we have is we have a d2 by dx squared of d2 uy by dt squared, so plus a 1 over rho naught, and then here we have a d by dy of rho naught d by dy of d2 uy by dt squared. And then equals minus n squared d2 uy by dx squared. And of course we could take the second derivative of x of time outside here. So second derivative of time comes out, so d2 by dt squared of here. So we have d2 uy by dx squared plus 1 over rho. We have d 1 over rho d by dy of rho naught d uy by dy, and that is equal to minus n squared d2 uy by dx squared. So that is the partial differential equation. It's a linear equation for these buoyancy waves. And you see it's a little more complicated, but essentially if you see the pieces from the old simple expression we had here. So we have this n squared, we have this term here, which is basically a second derivative in time. It's basically just this term here we've added. And so what we can do now is we can make some small assumptions and essentially simplify this a little bit. So here we have one assumption we can make, for example, is that the gradient of the wave, so the wave is this uy, is the perturbation, and this is assumed to be a small scale, so this term is large compared to, say, the gradients of the equilibrium. So if the equilibrium is varying slowly compared to the wave, then we can move this rho naught out and cancel with this 1 over rho naught. And so we can write down a slightly simpler but still good approximation just by moving these out through here. And then what we can do is we can say that uy is varying like, so it's some constant, and then we have an e, and then we have basically wave numbers in x and y and in time. So let's say kx plus ly minus omega t. So this is a wave in x and y and time. And so d2 by dt squared goes to minus omega squared. The same for x squared, d2 by dx squared becomes minus k squared, d2 by y squared becomes minus l squared. And so what we end up with is essentially an omega squared from here with a minus, which is going to cancel with the minus from here. So here we have k squared, so we have a d2 by dx squared, plus an L squared. From here we have a second derivative in y. Let's go have the constant. That constant is going to cancel out when we go over to this side. And then here we have a minus, and then we have d2 by dx squared becomes a minus k squared. So that just gives us an n squared k squared. And this is now the dispersion relation for this wave. So we have omega squared is equal to n squared k squared over k squared plus l squared, where k is the wave number in x and l is the wave number in y in the vertical direction. And using this we can find some slightly strange properties of this wave. So one in particular is that the phase velocities, which is the direction the waves appear to be moving in, so it's where the peaks of the wave are moving, and the group velocity, which is where the energy is going and where the whole group of waves is going, are in opposite directions. So in y, we can work out the phase speed. So phase speed in y is just omega over L, and this is, so we have an n, so a k over L, and then we have 1 over square root of this, so 1 over square root of k squared plus L squared. And so if k and L have the same sign, then for example this is greater than 0, and so we have a phase speed going up. So if k over L is greater than 0, so then we have a positive phase velocity, so up. So it's going upwards. Now if you look at the group speed, which is where the energy is going, so this is d omega by dl. And now we have a slightly different thing, that we have L is on the bottom here, and so we end up with this is C, so we have an n times a k, then we have a square root here, so this ends up as a k squared plus L squared to the 3 over 2, and then we have here, we have a minus, there's a half because it was a square root, and the factor of 2 because there's a squared here, so minus, we have it with an L, so times minus L. and so this is just equal to minus n kl over k squared plus l squared. And if these have the same sign, then this is less than 0, so this is going down. So the waves are going one direction, and the group of waves are going the opposite direction. And so if you have a parcel of waves, so say a Gaussian profile with some wave packets in some, the wave looks like this. The wave might be propagating down like this. So if this is the y direction, so the waves appear to be moving this way, but the actual parcel of waves will move the opposite direction. So this is the phase speed. So the phase velocity is going downwards, and the group, so group velocity is going upwards. So this is an unusual example of a wave dispersion relation where you have velocities in opposite directions. But this has important applications in atmospheric and oceanic physics, and some of these kind of behaviors occur in plasmas too.